Hello, everyone. It's a great pleasure to be here today. My name is Rick Wong. I'm a software engineer at Netflix. Now, in case you're wondering if you come to the right talk, I'm 99% sure that you are, because this is what the recommendations say so. In this talk, we'll take you to a journey into how Netflix encodes at scale. Now, you wonder, how does it matter to me? Well, we use ourselves as a use case, as a case study, so we can kind of figure out how we solve a problem. And in this talk, we would discuss about our challenges, the particular approaches we take, and of course, we'll share with you some of the learnings that we made, both positive and negative. And hopefully, they will resonate, and we can take it home. Maybe we'll also hear from some great ideas from you after the session. So, finally, at the end, we'll also ponder a little bit about what we might be doing in the future. With that said, let's have a quick introduction. Netflix is the world's leading internet entertainment service, with over 100 million members in 190 countries. We have a content budget of $6 billion in 2017 alone, and that results in 1,000 hours of original programming, with 400 original series and movies, along with a lot of great content, some licensed contents across the globe. All of these exciting contents are played on 1,500 internet-ready devices. Now, about our team, Media Cloud Engineering. Our team is responsible for handling all media processing in Netflix. That means anything that you watch on TV, it comes through our team. The infrastructure team in particular is responsible for building a distributed processing platform that is specialized in media processing. And this is what this talk is based on. Similar to now how Netflix brings binge-watching experience to our subscribers, our team's mission is simple. We want to bring binge encoding to Netflix. This graph was taken some time ago in October over a span of 2 weeks. And there is a number of interesting observations we can find in this graph. First, on the right side, you can see that we peak at 300,000 CPU hours. What does that mean? 300,000 CPU roughly translates to about 19,000 M4 4X large machine with 16 CPU each. That's 19,000 machines. And another interesting thing to observe is that this level of intense computing only happened on 4 days. If you see that on the left, most of the time, we don't use a lot of compute. We probably hover around 1,000 instances and whatnot. And that shows a little bit about the dynamic type of workload that we have to deal with. And when it rains, it pours. And the third thing I think is interesting to point out that it happened pretty recently. We have 3 color bands here across three different regions. It's only until recently we're able to do encoding across 3 regions. Doing so gives us a lot more capacity, but also brings us some new problems that we haven't thought of before that we will talk about later. All of this was accomplished by a very talented team that we have, that I work with every day, and we have a lot of fun doing this. Let's talk about compute capacity. We saw this graph that we have 19,000 machines. To me, that's a lot of machines. It costs us a lot of money. The first thing we have to ask ourselves is, why do we need so much compute? Are we really just doing it because we can? And what's the justifications for it? First, let's take a look at media assets. We have a lot of high-quality media assets arrived to Netflix from post-production partners. In 2016, when Netflix goes global, we have increased our global content catalog significantly. Every day we receive huge number of feature content, that is the movies and TV shows that we love. In addition, we have a lot of localized content. That is our language assets. This is very important assets that includes audio and subtitles. They are so important because this affects the user experience for our global members. Finally, we have a huge number of supplemental materials that are used for promotional, social, and in general, just to improve our user experience, such as montage and various assets. So what about encoding? How much encode do we need? Let's take a look at a great simple example. We'll use Death Note as an example. How many of you have watched Death Note? Okay, not many, so too late to change now. Anyway, Death Note is one of the Netflix production that supports Dolby Vision. So we have a Dolby Vision TV. If you want to enjoy the content there, what does it take to get there? Obviously, we'll fire up a video encoder with the Dolby Vision codec. And the output will be HEVC main 10 profile. For these discussions, let's focus on a single bitrate, 1750 variable bitrate. And the source material is IMF, interchangeable file format, which is a very high quality format. So after encoding, we have the output DRM'd and ready to go to the TV. Simple. It's a very simple linear process. There's a slight problem over here. This encode takes 51 hours. It requires quite a bit of patience, first of all, and not everybody here at Netflix is very patient. Now, the second problem is that sometimes bad things happen. The last thing you want to see is, at the 50th hour, the encode failed. What do? What if the material comes late and we got 24 hours to encode? That won't work. Retrying for another 51 hours is another pain point. For this title only, we see the multiplier that for every second, we take 30 seconds to encode for this particular codec and this particular bitrate. It changes depends on different codec and bitrate. So instead of doing it linearly, some smart people figured out how to break it up. Instead of encoding the entire thing from top to bottom, first second to last second, we break it up in 30 seconds. Each one of them can be encoded independently. And all the bits and pieces of the outputs are finally glued together and form the final output. And the rest of the pipeline looks exactly the same. Do you know what changes it makes with this organization? We change it from 51 hours to 15 minutes. So with this little change, it's great, assuming that you have enough capacities to do all 200 encode at the same time. So this is one of the reasons why we need a lot of capacity, so that we can be very swift, very agile. But this is just for one single bit rate and one single profile. In order to satisfy all 1,500 types of Netflix-ready devices, we support a lot of different codecs, a lot of different profiles. And for different bandwidth, we also support a bitrate ladder. So in reality, when we receive a single title, we do a bunch of stuff there. And that requires a lot of compute capacity. This is just one title. So if it's not Death Note, there will be some other favorite shows that you may like. And in practice, we oftentimes receive a lot of different titles at the same time. If it's a TV show, we may receive entire season. And sometimes we get lucky, we may get multiple seasons that arrive at the doorstep. And this is the reasons why when it rains, it pours. And when we receive the material, we want to be able to encode them as fast as we can. Now, we have a simple formula. Many is many. And this is what we do. So far, we talk about what we do for production. So from the source material all the way to your favorite playback device, a TV, or your phone. We haven't talked about research and development. In the world of encoding, there's a very fast change. It's very fast change pace. We always have new codec, new profile, and we have HEVC, HDR, Dolby Vision. We have VP9 for our mobile outputs, for high compressions and with great quality. And most recently, we engage in a lot of research and developments of AV1 codec. All of that requires a lot of iterative process to encode, assess, and reassess and re-encode to the point where we think the final output is of the quality that our members will enjoy. That takes a lot of research and development and compute capacities. In terms of innovations, our very talented video algorithm team came up with what we call VMAP, Perceptual Visual Quality, in addition to PSNR. We use this index to evaluate the encode to figure out what is the perceptual quality in a very consistent manner. And with this, we were able to detect any degradation of a video encode or any improvement. It is based on this tool we can evolve recently and do the dynamic optimization. We're able to do video compressions on per shot basis, given the premise that within the same shot, the pictures are alike, and then can find the optimal curve and optimal path to find the right resolutions, the right bit rate, and various additional parameters. And you will find the perfect one based on the VMAP. So we talk about video, audio, subtitles. When we think about media, this is what we're familiar with. That means we have 3 types of services, maybe. Would that be very simple? Well, what you're seeing here is the actual number of media processors that we have at Netflix. We mentioned that we can do chunk encode. Obviously, you have to have something to put it back together, so I have a video assembler. Now, if we can encode the video, we can also run the asset inspector. We do asset inspection to verify that the source material that we receive from a post-production partner is of the Netflix quality. We can do video complexity analysis so that we can do per title encode. So our bitrate ladder could be different for each title based on the complexity of title. So if you have animations, we may save a lot of bits because having more bits on it may not make any difference. And if we put all of this together and put it into one unique environment, that is the Netflix encoding services in a box. Now, this is all great for production value, but we also need to do development. Previously, we mentioned about research and development experiments, and we also need to do testing. We do weekly regressions. We need to figure out whether there's degradations between change of the video codec or algorithms or recipes. So what we actually do is that we wrap all these services together into, I got a picture of marbles. So just imagine that each one of them is a unique environment, that they're isolated, they don't interfere with each other. Anybody who's got a copy of this have full freedom to mess with it. You can do encode, try a new codec, write a new media processor without worrying about affecting production. And before you know it, we have 70 of those. We use a production canary. A/B testing is a special kind of production where we have limited release of a particular video algorithm, and then we do assessments on that. The development uses the majority of the farms, that every engineer get a few farms they can do full experiment on. So how do we scale in the cloud? This talk is based on the current Netflix media processing platform that we built. And we have a code name called Reloaded. That's why you see the picture here. It is a 3rd generation of the platform that was deployed since 2013. And it's completely cloud-based. And most recently, we're able to encode across multiple regions. I have a simplified architecture here because I don't want to bore you too much. It's so simple that will fit in a single piece of paper napkin. It is based on 2 very common patterns that we're all familiar with. The first is microservice. We all heard about that. It is a great way to build services. And as you can imagine, a video encoder is a microservice. It is single purpose, doesn't do anything else. It wouldn't know how to do audio encode. It is decoupled, and it's stateless. Being statelessness is a very important aspect of microservice in such a way, in terms of scaling, we can scale up and scale down instances without worrying about any history, any memory, affecting one another. So this is a very important thing. The next thing is message-oriented. It fits really well with a work pattern because we don't have a steady stream of work all the time. Work is always event-driven. It is not uncommon to have some services that have no work, and suddenly you get millions of jobs in a moment's notice. It is asynchronous. What I don't show you is that we have a workflow engine that will figure out what jobs need to be produced. And it is very easy for the workflow engine to pump down millions of jobs without being tied up, because sending a job does not mean the job will be run immediately. There's a little difference about what we do with message and queue. In this case, we have a priority queue. We will go into a little bit later why priority queue matters. Scalability. We're all about scale, and this talks about scalability. According to this definition, scalability is ability to scale up and scale down. Changes in size includes both. We really need to have a way to do this elastically. So in the previous example in the slide, we saw that we get up to 19,000 instances. In order to achieve that, we depend on Amazon Web Services. We use EC2 coupled with other scaling groups to handle all of our encoder and media processors. S3 is a persistent storage that we can use for security and durability. For all our input and outputs are all on S3. I forgot to mention Aurora. We use Aurora as a way to implement our priority queue. So this is a screenshot of our auto-scaling groups using our internal tool, Spinnaker. It is also an open source project. And in this picture, you can see that we have 50,000 thousand instances across multiple ASGs. They're all video encoder running in a farm on USCs. We use Spinnaker because Spinnaker gives us an abstraction, allow us to have the notions of an application that maps really well with microservice. I don't have to come up with my own scheme of naming ASG name. Spinnaker kind of takes care of that. The next example is to show how the Dolby Vision encoder scale up over a period of time. In this case, I think it's about 12 hours, and the video encoder, and they scale independently. Now, we talk about AWS, and we have auto-scaling groups, and we have microservices that maps really well with auto-scaling groups. So is this as simple as just filling up, and when we apply a auto-scaling group scaling policy, and we all go home and because we're done? Well, I would like that to be the case, but it's actually a little bit more complicated because of our unique environment. Let's start with how we map auto-scaling group and microservices to ASGs. This is how we will envision. We have each one of these ASG filled up with instances, and these are all microservices, and this is a picture that is very easy to understand. However, because our work is dynamic, we would like to ideally scale each of the ASG based on amount of work we have in each of the individual queue. In this case, you can see that video encoder has a bigger queue, and it would need more instances to finish this work in a timely manner. We know that EC2 is incredibly elastic, but we also know that we live in a world of EC2 reservations. For economy, most of us purchase the EC2 reservations, and because it saves us more money. Netflix reservations is the same. We do monthly evaluation, we make more purchases, but at the end of the day, at any moment, we have a pretty stable amount of reservations that we want to observe. In this example, we see that we have 10 instances. And let's pretend for the moment that entire Netflix has the reservations of 10 machines. We use them all up. And we noticed that the audio encoder increased in queue size. Now, what do? If we simply scale the audio encoder with a scaling policy, then we will go over our reservation and we'll pay for on-demand. A little bit small percentage of on-demand is okay, but if we consistently use this in a constrained manner, and it will catch up on you. So what we really want to do is to respect our reservation so that we don't scale up more than what we own. And also, ideally, we want to be able to share our instances across and distribute it evenly and fairly. At the same time, try to maintain the reservations not being overused. The next example is a little bit unique to us. So how many of you have watched Star Trek, the most recent Star Trek, Discovery? Great. How many of you are aware that Netflix also have an after-Trek show? Okay. So the Star Trek after show is broadcast pretty much an hour immediately after the Star Trek show. And we have a very small window that we need to encode everything within 30 minutes so that the language translator across the world can do subtitle translation. So we have such a tight window. So what happens if our video encoder has a lot of work? And we need to be able to do the most important thing first. And in this case, we may have just a few messages in deep color. Those are high priority messages. And then in this case, we have audio encoder having a lot of more high priority message than video encoder. We want to be able to ideally put more instances in the audio encoder than the video encoder because the number of high priority messages exceeds the video encoder. So in essence, we want to balance our resource not only based on the size of the queue, but also based on the priority in it. And the next thing I like to talk about is rebalancing instances. So I mentioned that in the worst case, in the previous example, we could spend 51 hours, but we don't. And a video encoder can spend from 15 minutes, and for certain codec and bit rate, it could go all the way up to an hour. So when we want to rebalance the instances, we really don't want to lose any work that is in progress. So if we simply scale down an ASG, and you have a chance of randomly killing any particular instance, and if you're unlucky, you will kill video encoder in case V1. The color bar shows the amount of progress that has been made. In this case, it's almost finished. And it will be a shame if this is the one that gets picked up. But you don't have all our choices. So that means we can't really just use a simple scaling algorithm just to shrink the ASG. And there are some ways to mitigate it. For example, we can save work in progress with some kind of checkpoint, but that's not possible for a lot of media processors. So the conclusion is that terminations of in-flight jobs can be expensive. We want to avoid that if possible. Putting it all together, we want to be able to share all the instances and resources across all the farms. Remember, we have about 70 farms. Each one of them has a bunch of ASGs in it. And oftentimes what we observe is that our demand exceeds supply. And we want to do it fairly. As if this is not enough of a problem, we have some additional constraints. We have capacity fluctuations. While the Netflix has a fixed number of reservations at the moment, but the number of instances that we can use depends on what's available, what is in use. So, for example, for the rest of the Netflix, we have API services that are directly tied to end-user experience and playback experience. And the last thing we want to happen is that we're doing some encode that would cause us rebuffering on some players. So we give ourselves the lowest priority. We constantly observe and figure out whether we are in competitions with the rest of the Netflix services, and we want to yield when that happens. That means that capacity fluctuates over time. We also have a lot of different instance types. And in order to make fully utilized all this capacity, we need to be adaptive. we have to be able to teach our microservices to be able to use different instance type. So we'll figure out how we approach that. Now, we have a revisions of how we look at a farm. In this case, a video encoder is not made up of one single ASG. Based on what we just saw, we have different instance types, and because the majority of our reservations are zonal, with some combinations of regional reservations, we have to observe our reservations by zone. So if you look at video encoder here, we may have a number of ASGs tied to a particular zone and particular instance type. And those are complexity that we're dealing with. Just checking if you're paying attention. And if you're looking at the remote, it's right here. Scaling strategy. So how do we do that? Now we're talking about how we approached the scaling problem. Well, we want to have a system that observes the weight of the job. For example, if for some microservices, if this is in production, it will trump anything that could be an experiment or testing phase. And we want to assign instances also based on the job pressure. So if you have a lot of job in particular queue, obviously you have a higher pressure, you want to get more resources assigned to it. But at the same time, we want to account for priority. Higher priority jobs will have higher weight. And finally, as we mentioned before, because we don't want to lose any work in progress, all of this has to be done gently. And we need to orchestrate any scaling up and scaling down. Scale up is easy if you have enough resources. But if you don't, you have to wait until one of the applications yields the instances before you can scale up. And all of that is done in a cycle, continuously. So at every cycle, we look at what we really want individually across the entire farm. And we have to look at what we have based on the ever-changing amount of capacity. Apply the delta, and then try to remediate it. And we do it continuously. This is a picture I found of a heartbeat. And I'm imagining that this is a healthy person's heartbeat. This is great for a person. But in terms of scaling, this is actually pretty bad. Because if you notice this, if we scale in this pattern, we'll end up spending more time scaling than computing. And that's not where we want to go. So in computing, we want to be smooth. We want scaling to be smooth and stable. It's a delicate balance. How do we do that? If we scale very quickly in this example, and we run the danger of overshooting, how do we know how many video encoder do we need? Do we need 1,000? Do we need 1,200? That's a very difficult question to ask. And if you make a mistake, you could easily overscale and then regret later, and then you shrink, and then you may end up overcompensating. Then you spend most of the time just scaling up and spinning down instances. The way we approach it is that instead of using a crystal ball to figure out how many instances we need, we use a smaller crystal ball to say, well, we think this is how much we need, but we're not quite sure. But we're not going to take everything. We just say, for example, we do a percentage of it. Maybe we just scale up or scale down by 10% of what we think we need, and then come back later in 10 minutes to look to see, hey, is anything changes? Is it helping? Do we need more? So being incremental really alleviate and help us to be able to scale more accurately in fact, and not having to be overly precise. So this is a very difficult game to be able to scale up and down in a delicate balance. So putting it all together, if you imagine we have 70 different farms, each one of them has 40-some type of media processors across 3 regions. We built our own custom autoscaler that understands all of this. We call it the world. And then what this scaler does is that it will maintain the deployment model. It understands what's been deployed, and it has a resource monitor that continually figure out how many resources are available for our encoding needs. Are we overspending? Because if we overspend, we'll also shrink and we'll scale down. And then, of course, we have the queue monitor. We also call it the barometer, that looks at every queue for every microservice in every farm, and we maintain that in order to help us and guide us into figuring out how much resource are needed. And all of this information are fed into the planner. We have a planner that makes plan every 10 minutes because we believe that things changes in 10 minutes. And the plans that are made are realized by the upscaler and downscaler. For any scaling operations that cannot be done immediately, we have an orchestrator to figure out how to wind down an instance, and when it finally goes away, we will wind up another instance in a different microservice. So in the gist, this is what we have. The next problem we want to solve is different instance type. Our goal is very simple. When we get an instance, when we know what's available out there, we want to use anything that's possible, and we want to use as many instance types as possible, and not having to leave too many things on the table when we can actually use them. But when we do have an instance, we want to make maximum use of it. Obviously, if you're landed on an M416XL machine with 64 CPU, and then you end up spending just 10% CPU utilization, it will be a big waste. We don't want to have to happen. And how do we do that? There are a couple of approaches. You can be very, very precise. You can match a particular instance type to a particular type of microservice and have a perfect match. But the problem is, asking an engineer to figure out which machine type to run for each microservice is very difficult. And because I try to ask myself how much memory I need, I don't know. Because anything that I observe for the moment may be wrong, or maybe I just don't have the right amount of data to come in that hits the worst case scenario. And if I do make an estimation, it can get stale, decay over time, could be wrong the next month. So what do? We usually overestimate just to be safe, and that results in very low CPU utilization. And there goes the efficiency. Finally, it's very complicated to implement this. If you have the autoscaler try to find a mix and match of many, many different instance types across 40 or 100 different microprocessors, it's a very difficult problem to solve. So instead, what we do is we try to treat the instance type generically. And let's leave aside for the moment that R3 and R4 has a lot of memory. Let's not solve the problem for the moment. We teach each of the microservice to self-inflate. Given a particular instance type, we just figure out the best way to maximize the CPU utilization. By doing so, we have a very nice side effect of oversubscription. Now, we no longer have to plan for the peak utilization. We can actually nudge the bar a little lower, hoping for the best that you don't hit the worst case scenario for every concurrent session. And if you do, we are able to recover from it because jobs are resilient. So only if you get incredibly unlucky that you run everything at the same time in a single instance and every one of the sessions is worst case scenario, that doesn't really happen in real life. And because of all this arrangement, now our estimation can be a little fuzzy. So let's look at video encoder as an example. In this case, we landed an M3 extra large instance. We run a single session in it. But if we get a bigger box, we'll run 4. And if we're more ambitious, we may run 5 just to see what happens. So give us a lot of room to tune it. And this is what I mean by oversubscription. So far, we talked about how we approached it. What about lessons learned? I would like to think that we all sit down and thought of everything and thought of best solutions at the beginning, but that's not the case. In fact, we learned a lot of things that based on what didn't work. So if there's one thing that I think I'd like our audience to get out in this room is that when you build something that scales very large, you have to be very concerned about the efficiency, about your API calls. For example, if I make an AWS call, S3 call, should it be 1 call? Should it be 2 call? Can it be combined? Every little bit of an inefficiency may not be revealed when you run several hundred instances, but we start going to the thousands, then suddenly you will notice it. Sometimes it's, you get throttles, Is your S3 key properly hashed in such a way that you don't create hotspots? You may not notice it when you run a very small amount of scale, but when you scale up, and you will notice it right away. Cost-wise, it's the same. If you're a little bit inefficiency about cost, you may not notice it until you start running tens of thousands of instances, and it will shock you. So let's give you a couple of examples where you learned. Our encoding we have been doing encoding in US East 1 for the last few years. All our assets are stored on S3 in US East 1. And we're pretty used to just grabbing the resources, reading and writing to the S3 buckets in the same regions, and that was easy. There was never a problem. But when we start going to two additional other regions, we thought we'd just cookie cut it. And we did notice that it cost, half a cent for a gigabyte, and that didn't feel like a big deal for us at the time, because based on our observations and the cost was reasonable. But what we failed to realize was that the recent change of the per shot encoding, it changes entire access pattern. So we received quite a shocker when we finally get the bill. And we looked at it and thought, oh, I wish I had thought of that. But because we're able to tune down and shut off the two additional regions until we find a fix, we're able to find a solution. The way we access our data, our files on S3, is through a file system that we implement. And we're able to use a regional file cache that, by putting a file cache, we store a block, a 16 megabyte blocks on the range get, we put it up there. And for any subsequent, repeated access of the same block, we'll fetch it from the regional bucket. This very simple change was done by a couple of three very smart engineers in about a week. And then immediately we observed that we gained 90% hit, cache hit. That means we're saving. We're only paying 10%. That we have to pull materials all the way from the US East to the US West or EU West. So this is an example that the cost can catch up on you if you don't pay attention. The next example is a true story. And if you get a call from the Amazon technical account manager at 2 a.m. in the morning, he doesn't call you to say, hello, Rick, how are you doing? He calls you to say, hello, Rick, stop doing what you're doing. And in this case, it happened. And we immediately tuned down our systems. But we cannot really shut off. Right? He asked us to shut down. But we didn't really shut down because we can't shut down our business. Unfortunately, we also have a limit, some kind of knobs that we turn and tune down our instances from 12,000 instances all the way down to 1,000 instances. And because our jobs are prioritized, we know that all the important jobs will be done first. Our downstream customer probably would notice it, even though we have a very big backlog. So we went to sleep, and before we found the solution at 11 a.m., I get an email that says that my shipping is delayed. So I called the TAM, and he said this is unrelated, but I don't believe him. So we found the solution of a hot fix at 5 p.m. You can see the little tick up, and we did a rolling upgrade. We observed it for 2 hours, and everything looked good. And we're back to business. So the lesson we learned here is, again, a little things can become magnified when you're running tens of thousands of instances. But fortunately, if you build enough switches, cut-off valve, shut-off valve, you can at least get by the day until you find a fix. So some words about microservices. We love microservices. This is what gets us where we are today, as you can see. We have very good partitioning of the problem in terms of microservices. Video encoder is different from audio encoder, and we can build many of those. But we also have some difficulties here. As you can see, we have about 45 microservices out there, And we start off with 10. But when we start to get to about 40, 45, we're starting to feel a lot of pain. That's in terms of software development life cycles. That includes build, bake, test, deploy, and it's continuous. So to manage all of this, it's very difficult. I mentioned previously that we want to do multiple sessions at the same time. That's great. We achieve a great efficiency, but we also force the programmers to have to understand concurrent programming. And how many of you think that concurrent programming is easy? I don't think it's easy, I'm sorry. But that's just me. And to have to think about thread safety is a distraction, in my mind, for the programmers who want to write the video encoders for this particular codec. And at the same time, we also forces the idea that they are building not a video encoder, they're building a video encoder service that needs to be 24/7. You want to make sure you have tried with resource. You want to make sure you release everything so that you don't leak memory, you don't leak file handle or anything that can cause you grief over time. And all of this becomes a distractions. And that might be the reasons why we don't have that many microservices. And finally, OS dependency is not being captured. The way we build today, if we have the image converter that require a very specific versions of image magic library, we have a difficult time doing that because everything is baked into one single image. So I think you can pretty much see where we're leading up to in terms of container. The next thing is about knobs. Knobs are great, and they save us quite a bit of time, except that if we tune by human, it's really hard, and we forget a lot of times. So today we have knobs on how to scale for each microservices. They have different behavior that we have to ask the human to give those parameters. So basically, it's a giant list of questionnaire you have to fill out. And we want to do better than that. But not everything is bad. Obviously, I think we did something good. Atlas telemetry. So we put a lot of effort into metrics, insight. And it is with this information, so we're able to tune the system in such a way that maximize efficiency. And if anything goes wrong, if we don't scale it correctly, we'll know that right away before bad things really happens. We talk about how we break up video encoding into little chunks of encode. That makes up small unit work. The result of doing that makes us a lot more agile. And we also can leverage the scalability to increase parallelism and speed up the final output. All our jobs are resilient. It is okay if you're running a job, we don't want to, but if you're running a job that failed and the instance died, it is okay because it gets recovered. And coupling with small unit of work and job resilience, we have small unit of recovery, which is a great thing to have. Job priority, as I mentioned, is really good. When we're running limited capacity, we can still get through the day without impacting downstream customers. So I'm so happy that we have that. Automations, we invest a lot of efforts in the automations. We believe in going home to see our family. And if we do it right, we don't have to be staring at the screen all the time. And I think that we have come a long way. There's still more improvement we can do in the future. Shuttle valves, as I mentioned before, or limiter. These are the things that we bake into the system. Every time we build anything new, we want to make sure that there's an escape route. Looking forward, we happen to be in a moment where we are thinking about the next versions of architecture, how we evolve, how we can make a systems more scalable. And we think of three very important qualities that we want to do. The first one, serverless computing. This is not just a buzzword. To us, it matters a lot because for us as an infrastructure team, we built this distributed computing platform. Our end customers are the ones that will have to write the video encoder and audio encoder. We don't want them to write a video encoder. We wanted to write a video encoding function for this particular profile and this particular codec. and to make it so easy that they just focus on their business, writing a function. And we worry about scaling it. We don't have to ask them to worry about how much memory do you need, writing a service that's 24/7 so it doesn't need memory and it won't die by itself. So those are all distractions we want to get away. Container technology, that's a bit of a no-brainer. We want to be able to encapsulate OS dependency. But another thing that is really great for container is that the cost of context switch is so much lower than spinning up and spinning down instances. And then you have a very stable allocation of instances, and you can just switch containers in it. So this is another great step that we can improve our efficiency by spending less time on scaling. Finally, I think that I already kind of mentioned it about this is, in order for function as a service to be successful, it has to be zero administrations. I don't want to hand out a questionnaire to all our customers and to have to tell us how much memory do you need, how much EBS volumes do you need, what is the I/O rate you need for the EBS volume. And that, again, these are distractions. If we're able to extract this out of our customers, the information is probably wrong a few months down the road. So those are the things that we want to invest a lot of time. And we're doing it right now as we speak. And we're really excited about that. These are all the materials I have for today. Today's Thursday, and we spent better part of the week. But we have a lot of great materials coming up from different talks from Netflix. And I encourage you to take a look at the rest of the talks on Friday and on today, and look at the videos of some of those, because we interact with all this team together to make this possible. This is all the materials I have. I'd like to thank you very much for coming. And I'm happy to answer any questions after the talk. Thank you.